In this next lecture, we'll focus on statistical models for time to event outcomes. In this case, they're called survival analysis models. And the idea is that you're trying to model how long the patient survived. Recall that in general, we're building regression models where there's some function of the outcome is equal to the intercept term plus some coefficients multiplied by the exposure plus some confounders. In the case of time to event outcomes, the outcome that we care about is the log of the hazard to an individual at a given time. This is known as a Cox regression, and it's named after the inventor, David Cox. Here, the estimate is the exponentiation of the coefficient from the Cox regression model, known as a hazard ratio. For a continuous exposure, this is interpreted as the instantaneous risk or hazard for a 1-unit change in the exposure, holding all the other variables constant. With a categorical exposure, the hazard ratio is the hazard among those with the exposure divided by the hazard among those without the exposure, holding all other variables constant. Or in the case of multiple exposure categories, it would be the hazard among those with the exposure divided by the hazard among those in the reference group, holding all other variables constant. Again, it is crucial to examine which, if any, of the variables are adjusted for, especially if the study was not randomized. But let's go back and look at this term, hazard. The hazard is the probability that a patient will experience the outcome at an instantaneous time after exposure, assuming that they have survived up to that point in time. So the higher the hazard, the more likely that an event will occur. And a hazard ratio is the ratio of the hazard between two groups. So a hazard ratio of 1 is what the null hypothesis means. In other words, that there's no difference in the hazard for the two different groups. So the null is that the hazard ratio is equal to 1. Generally, this means that if the confidence interval for the hazard ratio coefficient includes 1, it will not be statistically significant. And likewise, if the confidence interval does not include 1, it will be statistically significant. This is different than, say, continuous regression models where the null hypothesis is that the coefficient is equal to 0. Although survival analysis examines events over time, for a given study, the entirety of time is not measured, only a window of time. If a patient experiences an outcome during the measured window of time, they are considered to have an event. If they do not experience an outcome in the window, they are considered to be censored. This is because it is possible that they did experience the outcome, but it fell outside the window of time that was measured. This is why different techniques than basic regression modeling with linear regression are necessary. For example, if these 3 lines represent 3 different patient experiences, the first 2 would be considered as having an event because we observed what had happened, and the third would be considered censored. Recall the prospective cohort study we discussed in the study design section. This study looked at the impact of delirium and dementia on in-hospital death. You can find this article in PLOS Medicine. In their results, they report the unadjusted and adjusted hazard ratios with confidence intervals. Note that in this table they call their unadjusted hazard ratios bivariate hazard ratios. There is some heterogeneity in the literature as to how these models are referred to, but they often mean the same thing when they're talking about a single exposure term in the regression model. For example, we can interpret that delirium is associated with an increase in hazard of in-hospital death with a hazard ratio of 2.72, with a 95% confidence interval of 1.77 to 4.18 on the hazard ratio, holding all other variables constant. The hazard ratios we've been discussing are obtained from a Cox regression model. Often, in addition to a multivariable regression model, researchers like to visualize the survival analysis using something called a survival curve. These survival curves are really univariate analyses of survival data as they do not adjust for confounders. Here is an example of a survival curve. They are also known as Kaplan-Meier curves. The x-axis in this plot is time, so we will be measuring the outcome over time. And the y-axis is the percent of individuals that have survived at a particular time. So for example, in this plot, after about 5 units of time, only about 50% of the people have survived, and after 7.5 units of time, about 40% of the people have survived, and so forth. Each step in the plot indicates an event where a patient experienced the outcome. In other words, each time you see a drop in the plot, that is one case where a patient no longer survived. The plus sign indicates censoring, the time when the patient exited the study without experiencing the outcome. So if you see a lot of plus signs, it means we're missing a lot of those time points when we actually observe the event. The shaded region represents the uncertainty, often a 95% confidence interval for the survival curve. Often, you will see plots like this that show multiple survival curves to allow for comparison between groups. Again, recall that these survival curves are not adjusted for any covariates. For example, this plot shows the survival curve for an exposed group in red and an unexposed group in blue. Lower survival curves suggest that under that particular treatment, patients survived for less time. So in this case, the unexposed patients had lower survival than the patients who were exposed. Here is an example of a survival curve from the delirium and dementia paper. This plot compares 4 curves: no delirium and no dementia, no delirium with delirium, no dementia, and delirium superimposed on dementia. We can interpret this graph that there are observed differences between the unadjusted mortality probabilities according to the delirium and dementia diagnosis. Again, recall that this is a qualitative comparison between these different curves, and it has not been adjusted for confounders, but it does allow you to visualize the differences in a way that the regression modeling with the hazard regression is not as easy to see.